Shalom and hello to all present. My name is Inbal Gadish and I'm honored to talk about thermal comfort in public spaces of a densifying Mediterranean business district. Working as a regional planner in Ramat Gan municipality, I'm responsible for town planning in my case study area. Israel is located in the eastern part of the Mediterranean zone, which is a hotspot for climate change. Some of its geographical characteristics illustrate the need for optimizing the use of lands in the country. Our case study area is historic diamonds exchange and industry district called the Bursa. It comprises about 30 hectares of mainly office buildings located in the central metropolitan area in Israel, about 3 kilometers from coastline. A new master plan promoted by the municipality permits multiplying the 1 million square meters of existing built floor area by about 3.5 times, which may lead to an extremely dense LCZ1 all over the complex. The plan visions the district as a bustling multi-purpose urban center. Our case study streets are located in the northern densely built section of the district, characterized by LCZ2. We focus on two approximately perpendicular streets described on the right, including existing and predicted sections due to the new master plan. So, the main aim of the research is to estimate present and future thermal comfort conditions in the public spaces of a densifying business district in the summer, and the secondary aims handle with quantifying the thermal features of urban components, quantifying present summer thermal comfort conditions, evaluating future thermal comfort using sensitivity tests, and examination of customary approaches to reduce thermal stress. We use the index of thermal stress for the evaluation of the thermal sensations. It was originally developed by the late Professor Baruch Giv'oni, to whose memory this conference is dedicated. Some of you may know this index and be interested in several improvements we put into it for this work. It enables a comfortable and simple tool for the dealing with complex issues. Measurements were conducted in the end of June last year on a typical summer day. Thermal characterizing of horizontal and vertical street surface is a unique requirement of the ITS. Existing thermal conditions in all 4 case study streets were found as warm. Until noontime, there is no real difference between north-south streets and the perpendicular ones. But in the afternoon, these north-south streets are already shaded and they are cooler. We can also see that the wider north-south street is permanently warmer than the slightly twisted one. Sensitivity tests of many relevant factors enabled us to understand and quantify the specific pattern of influence of every factor by itself on thermal comfort. Air temperature has a linear effect. This type of impact is typical of many other factors too. Note that it takes about 10 degrees to switch from one comfort level to another, which implies the complexity of determining thermal comfort. Wind speed has a slightly exponential impact. As wind slows, the stress grows higher. Building height is unique for its dependency upon the geometry of the street and the sun position, meaning solar radiation. Note that the roughly east-west street was found thermally milder except for tests involving building height. We assembled the basic future scenario combined of the main variable of building height with correlated predicted changes in air temperature and wind speed attenuation. But although high construction is expected to ease the thermal stress, weaker wind and higher air temperature will worsen thermal comfort. All this refers to a hypothetical person who is in the center of the street cross-section. Comparing between ITS of basic future scenarios for a person standing in the sun and in the shade reveals the effect of sun radiation on thermal comfort. The bottom graphs clarify how hotter is the north-south street compared to the perpendicular one, even under high buildings. A combined influence of relative humidity with wind speed and air temperature reveals an extreme exponential impact on thermal comfort. Using cool materials for street horizontal surfaces is proven to decrease its temperature. We quantified its possible effect on thermal comfort. Trees improve environment and human welfare in many ways. ITS quantifies the effect of trees cover in the street on thermal comfort. Here we can see the quantification of the effects of customary strategies for heat mitigation on thermal comfort. Using cool materials for street surfaces and additive shadow of trees may be beneficial and decrease thermal stress, but note it is only tangible when and where there is exposure to solar radiation. Note darker colors in the graphs mark basic future scenario. Brighter tints indicate maximum practical trees cover, and the brightest are for the aforementioned plus cool materials. In summary, using the index of thermal stress to analyze a densifying urban business district, we found that solar radiation has a dominant impact on thermal environment in Mediterranean cities. Therefore, internal shading in street canyons can dramatically reduce pedestrians' thermal stress in summer. Taller buildings impair ventilation and exacerbate the urban heat island, but also improve shading and overall thermal comfort. Further research is needed in order to characterize the effects of glazing types and wind regime on thermal comfort in such a complex urban district. Also, a similar study is required for the winter season. Thank you very much for your attention.